Hi, in this video we can see an easy way to find the bond order by applying MO theory. Atomic orbitals are overlap and form molecular orbitals by the process of linear combination of atomic orbital approximation method. The molecular orbitals are obtained by addition of wave function. That means constructive interaction means it forms bonding molecular orbitals. If the orbitals are obtained by subtraction of wave function means the molecular orbitals are called as anti-bonding molecular orbitals, and that interaction is called as destructive interactions. So the number of atomic orbitals combined is always form equivalent number of molecular orbitals. Among the formed molecular orbitals, half of the molecular orbitals are called as bonding molecular orbitals. Then another half of the molecular orbitals are called as anti-bonding molecular orbitals. So whenever the atomic orbitals combine and form molecular orbitals, the atomic orbitals lose their individual identity. Next, before enter into draw the MO diagram for molecule, first we must remember the arrangement of the electrons in this condition. That means the electrons are arranged in some way. For example, if the molecule have then electrons up to 14 means at that condition the electrons are filled first in s orbital, then it enter into pi orbital. After fill in pi orbitals only we can fill the electrons in sigma orbitals. Suppose the molecule have greater than 14 electron means at that condition after filling in 2s orbitals, then the electrons are directly enter into sigma orbitals, then only it enter into pi orbitals. So to draw a correct MO diagram we must remember this order. Okay, now first take the example of boron molecule as the first one. So the electronic configuration of boron is 1s2 2s2 2p1. That means the atomic number of boron is 5. So the electronic configuration is 1s2 2s2 2p1. So the boron molecule have 10 electrons as totally. So in this condition we want to fill the electrons in s orbital first, then we want to move to the p orbitals. So after filling the s orbitals, then we want to fill the electrons in p orbital. Here the total number of electron is 10. So that first we want to fill the pi orbital, then only we want to fill the electrons in sigma orbitals. So after filling this electron we can calculate the bond order. The equation used to calculate the bond order is Nb minus Na divided by 2. Here Nb represents the number of electrons present in bonding orbital. Then Na represents the number of electrons in anti-bonding molecular orbitals. So in boron molecule, the number of electrons present in bonding orbital is 4. Then the number of electrons present in anti-bonding molecular orbital is 2. So by applying this equation we get the bond order is equivalent to 1. That means boron molecule is connected with each other by single bond. Then we can also predict the magnetic properties of boron molecule by observing the number of electrons present in its p orbital. Further, for boron molecule, here we can observe that the single electron is present at sigma x orbitals. So the magnetic property of boron is paramagnetic. Next example, oxygen molecule. The number of atoms of oxygen is 8. So that the electronic configuration is 1s2 2s2 2p4. So the total number of oxygen molecule is the total number of electrons of oxygen molecule is 16. So we want to apply the second order. That means in this condition after filling 2s orbitals the electrons then enter into sigma 2 px orbital, then only it enter into pi orbitals. So we must remember this condition. So according to the arrangement of electrons, first we want to fill 2s orbitals, then we want to move for the 2p orbitals. So here we can see that because of the total number of electrons greater than 14, first we fill the electrons in sigma orbital, then only we fill the electrons in pi orbitals. So we can count the number of electrons present in bonding as well as anti-bonding molecular orbitals. So applying the equation, we can get bond order is equivalent to 2. So oxygen have double bond within it. Then you can also observe that the number of electrons present, its condition is single one. That means the lone pair of electrons are present, so that the magnetic property of oxygen molecule is paramagnetic. So now we can let us move for the simple trick. So whenever we have some molecule and we want to calculate bond order, just count its total number of electrons. For example, here I given 3 molecules, O2 plus, O2 and O2 minus. Just remember each number of electron, total number of electrons. Then we can easily predict the bond order. So in first condition, the total number of electron is 15. So the bond order is 2.5. Next, if you take O2, the total number of electron is 16. So we can fill the electrons according to the second arrangement. Then we can get the bond order is equivalent to 2. If you take O2 minus, in that condition the total number of electron is 17. So the bond order is equivalent to 1.5. Now we can move to find the easy way to calculate the bond order. So whenever we have some molecule, just remembering its total number of electrons, we can easily predict the bond order. So whenever we have molecule, just count its total number of electrons. Here the 14 is the midpoint of the scale. So for molecules, those have the total number of electron is 14, that bond order is 3. So from that midpoint, you move for the ascending order or for the descending order, automatically the bond order is degrees. So by simply remembering this scale, you can easily predict the bond order of the molecules. Thank you for watching.